Hello humans. So we're going to have a little video about solids, liquids, and gases and why they're different and why they're the same or similar. What you just saw in this little pan is some fuel that we're going to use to run this stove in a minute. We're going to heat up some air. So a lot of people would call what we just burned gas, but it was a liquid to start with. The reason it vaporized was because we added a little bit of kinetic energy in the form of fire. We've got a container that's got 610 grams of fuel in it. We're not going to use all of that fuel, but the mass beforehand is going to be greater than the mass afterward, because some of this liquid fuel is going to turn into a gas, and then we're going to burn those vapors. When we say gas in this video, we don't mean gasoline like in your car. We mean gas as in molecules are spaced widely apart. This is a little pump. We've been using the bicycle pump in class. This will add air to this fuel container. And the reason it's going to add air to the fuel container is because we want the air pressure, the molecules that are trying to get out, to push some of that fuel out of this little opening right here. Let's get the stove hooked up. So what we've got fuel container that's going to be pressurized with atmospheric air. We're just going to pump some extra air in there. And then we have a little burner. Let's see if we can get this rotated around. So the fuel canister is going to be off to the side. Let's go ahead and pressurize this. We're going to add some air to this container. The container is not going to get any bigger though. So we're squeezing those molecules of nitrogen and oxygen and carbon dioxide, just whatever's in our atmosphere. We're squeezing them into a space that is not getting any larger. So the volume inside this fuel container doesn't change, but the amount of molecules is being increased. So they're getting crowded. They're in there, they're pushing against each other, they're running into each other. And that's gonna allow us to run some of that liquid fuel out here. So I'm gonna go ahead and get this thing started. We've got a demonstration at the end. We're going to heat up some air and maybe get a balloon to fly for us by lowering the density. But we're going to get this started because it takes a minute to heat up. So I'm going to open a valve. A little bit of liquid fuel is going to run into the pan. You may be able to hear some gas coming from the stove. And maybe not. There it comes. So at this point, right down here underneath the stove, there's a little bowl, and a few drops of the liquid fuel have landed on there. And what we're going to do is we're going to give them some kinetic energy to get them moving faster. And oops. So now the liquid fuel that's in the bottom is burning, and it's heating up this pipe. And what's going to happen to the liquid that's inside the pipe as it gets to the boiling point? That's right, when liquid boils, the next step is to turn into a vapor. And you can see in the top here, there's some tiny flames coming out of the middle there. And when that gets going good, we're going to open up the valve again. And instead of liquid fuel going to the stove, it will become a vapor. So this pipe right here, when it gets hot enough, instead of burning liquid, we'll be burning evaporated fuel. Okay, let's see if that's enough. There we go. So at this point, the liquid that was in the tank is running through this hose. This metal pipe is being heated by the flames, so all the liquid fuel that comes through this pipe is vaporized, turned into a gas, and the gas comes up, mixes with the atmospheric oxygen at a great kinetic energy, and we have a chemical reaction. Ooh, interesting. Can you tell that the steel right here is glowing from the kinetic energy? So the heat is causing those molecules to vibrate fast enough that they're glowing. You know, since we've got that part running already, I think we should go ahead and see if the balloon will launch. So I've got a little chimney tower here. And all that is for is to direct the heated air upward. We've got a paper balloon that has a mass of 40 grams, and you can tell it's more dense than the air around us right now. But if we heat up the air molecules that are inside, they're going to bump against each other, and when they do that, they're going to try to take up a greater volume. If they take up a greater volume, but they weigh the same, they have the same mass, then the density goes down. So we're holding this over the heater. Oh. We're causing the molecules of air inside the paper balloon to heat up, start to bump against each other, take up more volume, and when they have more volume, that means that they are going to have less density. All right. Let me see if I can get this camera to move. So we've heated up the air inside. Let's see if it'll go up. That may not be coming back. All right, let's check out the rest of this stuff. Okay, so our stove is still going, and I'm sure our chimney is quite full of kinetic energy in the form of heat. I'm going to set this off. I don't think we need this anymore, so I'm going to go ahead and turn the liquid fuel supply off. And without any more reactants, that chemical reaction is going to slow down and stop. Now I'm going to set this out of the way so I don't get burned. All right, so there's one thing. All right. So in the classroom, we have been looking at this block of metal. It's just a sample that we keep in the classroom. But I would like to show you that solids can be turned into liquids. All we have to do is increase the kinetic energy. That means make the molecular motion get faster than the bonds between the solid parts can stay and hold together. So we're just going to take some heat. Different lighting here. So as we increase the kinetic energy, the molecular vibration, the bonds between the metal atoms starts to loosen. Now, it doesn't become anything else. This is not a new substance. Let me grab this. This is not a new substance. It's just a little bit of the metal melted, ran down, and then because it cooled back off, it froze, but it's still the exact same material as is in the larger block. That should be cool enough to touch now. So it's still the exact same material, we just melted it and it refroze. Just like if you had an ice cube, you could melt the ice cube, remove the kinetic energy, cool it down, and it would freeze again. Let's get that chunk of solid metal out of the way. This is an alcohol burner that you're going to be using in class. And we are not going to take these apart in class. If you need them to be serviced, like if you run out of fuel, you'll just bring it to me. I'm going to demonstrate to you what the fuel does just in this little metal pan. You can see so there's some liquid in there, and as the liquid heats up, it evaporates or vaporizes, and then because it's so hot, the kinetic energy causes the molecules with the oxygen to bounce against each other hard enough that we have a chemical reaction. We call it burning. But when we use these in class, very similarly to how the other fuel stove worked, this is a metal tube. It's got two little tiny holes. Matter of fact, you can see there's some bubbles coming out of that little hole where I put the lid on. The fuel, the alcohol fuel that's on the inside, has to evaporate before we can use it as a heat source. So when we use these alcohol stoves, and we've got a little bit of a breeze out here, when we use these alcohol stoves, you're probably not going to be able to see these flames in the building. So when we've got all the classroom lights on, that flame is just about invisible. You may see it a little bit, so make sure that whenever you are using these, you don't stick your hand over the little wire or over the little tube. If you want to put them out, you take the lid simply and put it on top, and what happens is the lid keeps the atmospheric oxygen from getting to the fuel, and so there's no more flame. So anytime that there's a lid on there, you know that this alcohol burner is not lit. But once again, we went from a liquid, we heated the liquid up, it evaporated or vaporized, comes out of little holes, and then we were able to have a chemical reaction. Alrighty. So one more thing, and we will do this again in the classroom. But these are the test tubes that we use. They're made of glass. Now, can you tell by looking at this piece of glass whether or not the molecules have a lot of kinetic energy? And by that I mean, is this hot glass? You can't really tell by looking, okay? Hot glass, cold glass, they look the same. So in the classroom, we're going to use little clamps, but I do want to show you that even though this is solid material, we can turn this into a liquid. How can we turn this into a liquid? By adding some kinetic energy. I'm going to put on an oven mitt. And I hope that this is easier to see out here than it is in the classrooms. It's a little bit dark out here. So we're going to add some kinetic energy. Heat up this glass a little bit. Now, when the glass gets this hot, you may be able to tell that it's hot glass by seeing that it glows, okay? Let's make this glow all the way around and see if we can get it into a semi-liquid state. All right, I'm gonna take a little pair of pliers here and see if we can, oops, that one broke. Let's get another one. And I gotta say, the reason I brought out more than one is because they break. All right, let's try this one. Maybe we won't use the pliers. We just heat it up enough, the solid will begin to soften, trying to turn to liquid. It's rather cool outside, and so if we take the flame off, then the glass goes back to a solid state. So just like the metal did, we heated it up till it turned liquid, and when we take the heat away, kinetic energy leaves, the molecular bonds settle back down because there's less molecular vibration going on. All right.